The Global Positioning System, better known as GPS, is a radio navigation technique based on satellites. These send data to the Earth in such a way that a device like our cell phones can receive it, and by using this information and a little geometry they can calculate its location in a frame of reference with an accuracy of 4.9 meters. It sounds relatively simple, however, we must consider that satellites move at speeds of 14,000 kilometers per hour, and not only that. Since the signals sent travel at approximately the speed of light, a synchronization error of just 1 microsecond could generate a miscalculation of almost 300 meters in the location. For all this and much more, in this video we will see how GPS works. The first thing to clarify before going into more detail is that GPS is a technology developed by the US Department of Defense, and that name refers only to the set of satellites that they manage. The generic name for this technology is actually GNSS or Global Navigation Satellite System, and there are several other similar satellite networks, such as Russia's GLONASS, the European Union's Galileo, India's NavIC, and China's Beidou. With that out of the way, the key concept on which GPS works is trilateration, a mathematical method for determining the relative positions of objects using geometry. Suppose we have a phone and a satellite on a plane. On the one hand, the information we know is the position of the satellite and its distance from the phone, while on the other hand, the information we want to obtain is the location of the phone. Using a single satellite, there will be infinite possible locations where the phone could be, and it must be somewhere on this circumference. If we consider a second satellite, for which we know its location and the distance between it and the phone again, things would improve a bit. This time, the only places where the phone could be found are at the points where the circumferences intersect, which means there are two possible locations. Finally, to be 100% sure of the location of the phone, we add a third satellite, and following the same logic, there will only be one place where the circumferences of the three satellites meet. Now that we understand this, let's see what would happen in an example that's closer to reality when considering a third dimension. This time, the possible places in which the phone could be found around the satellite will no longer be a simple circumference but a sphere, and because of this we will once again lose the clarity of the phone's position. As we can see in this example, there will be 2 points in space where the three spheres intersect, and similar to what we did before, the way to eliminate this uncertainty is to add one more satellite that gives us information of its position and distance. Considering all this, only one detail is missing to bring this mathematical model to reality: a coordinate system that allows us to determine the location of any point on our planet. In particular, the system used by GPS is called World Geodetic System in 1984, or WGS-84 for short. In this system, the origin of the coordinate system, through which all axes will pass, corresponds to the center of mass of the Earth. The z-axis corresponds to the conventional Earth pole. The x-axis corresponds to the intersection between the equatorial plane of the conventional Earth pole and the Greenwich meridian. And finally, the y-axis corresponds to the cross product between the z-axis and the x-axis. Now, going back a bit, if we only need the information from 4 satellites to know the position of a receiver, why are there 31 operational satellites today? There are mainly 2 reasons. The first is that this system must operate globally. We must remember that the location of the receivers must be obtained along the Earth's surface, and the signals emitted by the satellites can be received by them only as long as they have a direct line of communication. Thus, by positioning at least 24 satellites at an altitude of about 20,000 kilometers, which also move in 6 orbits around the planet Earth, it is ensured that each receiver has at least 4 satellites visible at all times, no matter where it's located. And the second reason is the robustness of the available information. A greater number of satellites makes it possible to have more information than necessary, making the system more robust in the calculations in case any of the satellites are lost or the signals have an error. At this point, it would seem that the greatest complexity of this type of system lies in its mathematics, but the truth is that we still have another problem. In the previous examples I told you that we knew the location of the satellites and the distance between them and the receiver. However, in reality the distance must be calculated using other information. If we consider that the satellite sends an electromagnetic signal to the receiver, and this signal travels at the speed of light, approximately 300,000 kilometers per second, then we can calculate the distance between them by measuring the travel time of the signal. Although to calculate the travel time of the signal we only need to know the exact time in which the signal is emitted by the satellite and when it reaches the receiver, this is not at all easy, because we must consider multiple variables that can affect the results of this calculation. Some of the most important are the level of accuracy of the instruments, the desynchronization of the clocks due to time dilation as explained by Albert Einstein's theory of relativity, and the effect of atmospheric layers. First, regarding the accuracy of the instruments, since signals travel at the speed of light, we must use a clock with enough resolution to calculate the distance accurately. To give you a concrete example, since signals travel at 300,000 kilometers per second, a difference of just 1 microsecond in the measurements would mean an error of 300 meters in the distance calculation. The solution to this problem is to use atomic clocks with resolutions of up to nanoseconds, which would theoretically result in errors of a maximum of approximately 30 centimeters per nanosecond of difference, a totally acceptable error for a geolocation system. The second variable to consider is the synchronization of the clocks. Suppose we have two atomic clocks, one at the receiver, on the ground, and the other inside the satellite. Because of the high speed moving relative to each other and the perturbation of the Earth's mass on space-time, the effects of the relativity of time must be considered. More specifically, even if both clocks have started completely synchronized, after only one day there will be a difference of 38.4 microseconds between their values. Such an error in the calculation of the distance between the satellite and the receiver means a difference of several kilometers, and moreover, this error will continue to accumulate as the time passes. Fortunately, thanks to the knowledge of the theory of relativity, it is possible to predict the time desynchronization with sufficient accuracy and thus electronically adjust the values delivered by the atomic clock. Finally, the third element to be considered in the calculation of the distance is the effect of the atmospheric layers, or rather, of the refraction of the signals as they pass through them. Just as when we look through a glass of water and the light is distorted, when a signal is sent by a satellite at an altitude of 20,000 kilometers, it has to pass from the vacuum of space through each of the layers of the atmosphere before finally reaching the receiver. Because of this, the signal experiences slight deviations in its trajectory, as well as a reduction in its propagation speed, and for this same reason the travel time of the signal will be affected as well. To solve this particular problem, mathematical models that are able to predict such delays, and thus consider the necessary corrections, have been generated. At this point, there is one element that we have completely ignored so far, which is the fact that our phones clearly don't have an atomic clock inside them. So how do they manage to know the travel time of the signals to calculate their location? Well, the solution to this problem again is mathematics. In particular, we must accept that the arrival time read by the electronic device will have an error due to its limited accuracy. And since this error in the arrival time is the same for the signals from all satellites, we can use mathematics to estimate. In other words, this error becomes an unknown to be determined. Thus, we will have four unknowns: the three spatial coordinates and the temporal error. Then, using the information from at least 4 satellites, it is possible to use the mathematical technique known as least squares, which, in a very simplified way, finds these unknowns by asking what values they should have in order for the equations describing the spheres to have the least possible error. If you liked this video and want to know how GPS signals arrive from space to our phones, I recommend you watch my video on how antennas work. That's all for now, and see you in the next video.